welcome to Boo Monday. Today we're going to be tackling different forms of geometry. We've got spherical geometry, also known as elliptic geometry. We got Euclidean geometry, and we got hyperbolic geometry. The first thing you'll notice is the curvature of each of these shapes. On a spherical plane, for straight lines, there is positive curvature. For Euclidean geometry, well, there's no curvature, as we're seeing this on a Euclidean plane. And for hyperbolic geometry, well, it bends in the opposite direction of spherical geometry, which allows it to have negative curvature. But what does all this mean? And how can it be utilized? Well, let's see. Let's take the north hemisphere and the south hemisphere of the sphere and put them right here. Just take the lines. In spherical geometry, these lines are actually parallel because they're curving around a sphere, which means they would meet at 90-degree angles. However, the lines converge, which means after a while, even if they're parallel, the lines would meet. This completely nullifies the parallel proselyte, in which for two angles, if they are interior angles and their addition of angles is less than 180, so then these lines will meet. As you can see, they met on point P. But for spherical geometry, no matter what, if you draw any amount of line on a sphere, and it has to be on the face of the sphere or the circle, they will meet. These two meet. However, for hyperbolic geometry, because hyperbolic geometry is basically the opposite of spherical or elliptic geometry, their lines actually diverge when parallel. This completely disobeys the parallel proselyte, in which if angles are less than 180 degrees and are interior angles, they will meet. Let's take a look at that. As you can see, these two angles call them A and angle B. A plus B is less than 180 degrees. That makes sense, right? So, surely, according to Euclid's axiom of the parallel prostylate, these two lines should somehow meet at a point. Well, through the trajectory they're going, it doesn't look like that's going to happen. In fact, for hyperbolic geometry, there are very few scenarios in which the lines will intersect. If they are parallel, they can't intersect, which means you have to draw non-parallel lines that, when combined, have an extremely small sum for them to even meet. Let's move on to the circumference of a circle in each of these planes. Let's say this is x. What will the circumference be for each of these geometries? Well, for spherical geometry, C is actually less than pi x. For Euclidean geometry, C equals pi x, or circumference equals pi x. And for hyperbolic geometry, the circumference is more than pi x. Let's look at another example. Let's look at a triangle. Let's start off with a nice Euclidean triangle, the one you know. A, B, and C. You'd expect A plus B plus C to equal 180, and you would be right. You would be correct. Now let's, draw a triangle on a sphere. Let's start off with the sphere. Well, wait a minute. The triangle's not straight on a Euclidean plane. In fact, it's curved. This is the difference in planes. Because the triangle is, curved on a sphere, that means that once again, the lines are convergent when with a parallel. Let's get back to A, B, and C. Let's keep it in the same order as this triangle. So, what do you think a plus b plus c equals? Well, it's not 180. It's not less than 180. Well, what could it be? Well, it's more than 180. Which means we could have a plus b plus c could have a sum of infinity. For a triangle. Now, what about hyperbolic geometry? Well, once again, the triangle is different. As you can see, the lines are divergent. Which means if we were to draw a parallel line for each of them, they would not meet at all. Now let's get back into a plus b plus c. Well, seeing how hyperbolic geometry is the opposite of spherical geometry, what do you expect? Is it more than 180 degrees? Nope. Well, does it equal 180 degrees? Nope. A plus b plus c is less than 180 degrees. That is correct. But that begs the question, could a plus b plus c equal 1 over infinity? Yes. Yes, it can. Could it be negative infinity? Well, we'll get to that another time. Let's get back these triangles. We're no longer doing the addition of angles. No. We're doing the area. Now for the area of a triangle in Euclidean geometry, we typically use Heron's formula. Where a plus b plus c divided by 2 equals s, or the surface area, and s times s minus a times s minus b times s minus c equals area. What about this hyperbolic triangle and this spherical triangle? Well, it's a bit different. And it's a lot simpler. For spherical geometry, a plus b plus c minus pi equals area. While for hyperbolic geometry, it's the opposite. Pi minus a plus b plus c equals area. Alright. That's well and dandy, but what if I didn't want to find the area of a triangle? What if I wanted to find the hypotenuse of a triangle? Well, we use Pythagorean theorem. A squared plus b squared equals c squared. Simple, easy, and correct. Now, for spherical and hyperbolic geometry, we're actually bringing out cosine and hyperbolic cosine. So cos A plus cos B equals cos C. Cosine A plus cosine B equals cosine C. That is how you find the hypotenuse. Well, cosine is the adjacent side over the hypotenuse. And cosine is e to the power of x minus e to the power of negative x divided by 2. Well, it's e to the power of x plus e to the power of negative x divided by 2. That's what cosine and cosine. Let's do one more example, of course. And that example is the diameter. Let's start off with the diameter of a circle, or diameter of a sphere in spherical geometry. Let's just take all these others. Diameter looks the biggest. Let's take the diagonal. Let's compare it to other ones like this and this. Diagonal well, let's actually do it like this. All lines are equal. Now for hyperbolic. The diameter looks the smallest. Make sure to like and subscribe. And I'll see you on next Boo Monday.